everybody, welcome to my latest video, which is mainly aimed at supporting the classes that I teach, but of course anyone is very welcome to have a look at them at any time. The work that I've been doing with my class on radians as a measure of angle has now got to the point where we can look at one application of it, and that application is all about small angles. And when an angle is small, you can actually simplify some of the trig functions. That makes it a lot easier to work with the algebra. You have to be a little bit careful about it, but it is on the syllabus, so there will be exam questions that will expect you to know this. Well, I hope you recognise this as being the sine function, but if you look carefully at the x-axis, it hasn't got the usual first maximum there at 90 degrees. It seems to be just a little bit more than 1.5. Well, this is because it's measured in radians, and 1.5 is half of 3, obviously, and in fact it's pi radians, which is 180 degrees, so pi by 2 gives you the maximum point there. So it's your same familiar sine graph, but with the x-axis measured in radians. Okay, well this is where the magic starts. I've superimposed the graph of y equals x, which as you would expect is going through -1, -1, the origin, 1, 1 and so on. And you'll see near the origin there's very little difference between the graph of the straight line and the graph of the curve. If we zoom in a bit on this, there we are, you can see we've zoomed right in there, and there is hardly any difference between the red curve and the kind of olive straight line. So when theta, the angle, is very small, the two are very, very close to each other. So we can express this as a little piece of algebra that sine theta is approximately equal to theta. That's what that sign means if you've not met that before. But you must read the top line very carefully. It's only when theta is measured in radians. It doesn't work in degrees. Okay, let's have a look at tan now. There's the graph, and I've already superimposed the line y equals x on top of it. Again, the only unfamiliar thing about that is the scale on the x-axis, because it's measured in radians. But if you look again at the origin, that branch of the red curve and the olive line are very close together. Okay, so once again we've zoomed in, and you can see there is very little difference between the curve and the line when the angle is small, when it's close to 0. So once more we can express this algebraically. Let me emphasise again, only when theta is measured in radians, only when theta is small, and then in those circumstances you can replace tan theta with just theta. Okay, cos is different to sine and tan. Clearly, if I was to draw the line y equals x on this, it's nowhere near where the curve is. But if you just focus on that little bit of curve when x is 0, where there's the maximum there, obviously the maximum of cos is 1 there. Imagine trying to fit a quadratic curve into that. Clearly the quadratic would have to have intercept of 1, so you'd want c to be 1, and the coefficient of x squared you would want to be negative, so that it sort of snugly fits into there. Let's have a little look and see what happens next. Well, I'd call that quite a snug fit, quite frankly. This is actually y equals 1 minus a half of x squared. And now let's have a little zoom in and see what happens. Well, there we are. It fits in, as I described earlier, snugly. It's not a line this time, it's a curve, but as ever, there's very little difference between the cos curve in red and the olive quadratic. So there's the algebra. I make no apologies for emphasising it's only when theta is measured in radians, and it's only when theta is small. Could be small negative, small positive. So finally, here's a summary of all three of those. Obviously the sine and tan ones are really easy to remember. Cos 1, just got to be a little bit careful with that half. You might prefer to write it as 1 minus theta squared divided by 2, but if you do that, don't forget it's only the theta squared that's divided by 2, it's not the 1 that's divided by 2 as well. So there you have it. Not a huge part of the A-level syllabus, but it's quite a useful little tool, and it's used in physics as well. I seem to remember something to do with the equation of the swing of a pendulum uses that approximation. So there we are, useful little bit of maths, maybe worth 2 or 3 marks in an A-level. Bye now.